Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 1. Limits and Continuity. Section 2.3. Calculating Limits.
Lesson 2. The limit of polynomials and rational functions.
All right, I want us to look at a rather important example because it will help us to find limits of many expressions very quickly. We're going to look at this next example, limit as x approaches 3, and I have a rather complicated function here, 5x squared minus 4x plus 7, so we want the limit of that as x approaches 3. We're going to do it in a very step-by-step manner, applying all the limit laws that we've looked at already, and then we're going to see how to do it very quickly. But for the time being, to understand why we can do it the fast way, I want us to do it step by step. The first thing I'm going to do is to break this up. Notice that it's a difference and sum of functions. We have 5x squared minus 4x plus 7. So I can use my difference law and my sum law to break it up into a difference and sum of individual limits. So this would be the same thing as the limit as x approaches 3 of the first term, 5x squared, minus the limit as x approaches 3 of the second term, 4x, plus the limit as x approaches 3 of the last term, 7. And there I'm really applying the sum and difference laws. Now let's look at each of those limits and see if we can reduce them further. If I look at this first limit, the limit as x approaches 3 of 5x squared, notice that I can apply the constant multiple law. I have 5 times x squared. And remember what the constant multiple law told us. It said that we can take a constant multiple, and 5 is a constant, and it is multiplying the x squared, and pull it outside of the limit sign. So this limit becomes the same as 5 times the limit as x approaches 3 of x squared. We can do the same type of thing for this second limit. I have 4 times x. 4 is a constant multiple, so I can pull that outside of the limit sign. And this would be the same as 4 times the limit as x approaches 3 of, and what I would be left with is just an x here. The last limit is actually just the limit of a constant, so that will be one that we can do easily. So let me just copy that down and we'll do it in the next step. Limit as x approaches 3 of 7. Okay, so let's see if we can find the limits that are left. I've got 5 times the limit as x approaches 3 of x squared. Well, on the last page, we said that when we have a power of x, the limit of the power of x can be computed just by replacing x with the number that it's approaching, namely 3. So limit as x approaches 3 of x squared, I replace the x with a 3, and I get 3 squared. The next term we have 4 times, and I have the limit as x approaches 3 of x. That's just the obvious limit, and so I end up with 3. Plus, my last limit is the limit of a constant. Limit as x approaches 3 of 7, and we said that one of our building block limits was limit of a constant. The limit of a constant is just equal to that constant. So the limit as x approaches 3 of 7 is just the number 7. Now we go ahead and compute this. I have 5 times 9, that would be 45, minus 4 times 3 is 12, plus 7. So that would be equal to 40. So the limit of my original expression is equal to 40. Now what I want you to do is to notice this particular line in the calculation that we did. Everything we did is fine, but it takes a long time. We used all of our limit laws to break it up into a sum and difference of limits, to pull out the constant multiple in each of these cases. And if you look at this particular line and compare it to our original function, notice that all that has happened is that we have replaced the x in our original function with the number that x is getting closer to, with x equals 3. I had 5x squared minus 4x plus 7. And notice that down here I have 5 times, if I replace the x with a 3, I get 3 squared, minus 4 times, if I replace the x with a 3, I get 3, plus the constant number 7. So really all we've done is to take our original expression and plug 3 in place of x. So a quicker way to do this whole problem would have been to just replace the x in my original expression with a 3 right at the beginning. So the alternative way would be to say, if I want the limit as x approaches 3 of 5x squared minus 4x plus 7, at least in this particular example, would be to say, that's the same as replacing all the x's I see with 3. 5 times 3 squared minus 4 times 3 plus 7. And then computing that and saying, that comes out to be equal to 40. Well, just replacing the x with a number that x is getting closer to won't work in every example, but let's think about what types of problems it would work in. What type of function was this that we were originally given? 5x squared minus 4x plus 7 is a polynomial. So notice that the function that we were given is a polynomial. If you think about another problem with another polynomial, notice that we would use exactly the same limit laws. We would have a sum and difference of terms with x to different integer powers, or possibly with a constant, and we would break it up in exactly the same way. And because we would break it up into constant multiples times powers of x, and we know that we're allowed to do the limit of a power of x by simply substituting for x, any polynomial would end up being done in exactly the same way. In other words, any polynomial we can find the limit of by just replacing the x with the number that the x is getting closer to. Let's go ahead and look at the next page, and we'll try to summarize what we've just discovered in a little bit more general setting. So in general, let's suppose that p of x is any polynomial, but I want to emphasize that we are just talking about polynomials. If we want the limit as x approaches some particular number a of p of x, we could do it step by step by breaking it up into sums and differences of terms, by pulling out the constant multiple outside of the limit sign, just as we did in the previous example. But in the end, we would end up with constant multiples times limits of powers of x, and we know that we can find the limit of a power of x by simply replacing x with the number that it's getting close to. So in the end, we could find the limit as x goes to a of any polynomial by simply replacing the x in the polynomial with the number a. In other words, we could find p evaluated at a. In the little red cloud over here, another way to say exactly the same thing is to say that we would just plug in a in place of or for the x's that we see in our polynomial. This rule is called the rule of direct substitution. It does not work for every limit problem, substitution, but it does work whenever we are finding the limit of a polynomial. Okay, I want you to take a moment, stop the video, and see if you can think about doing the next example, and then we'll go ahead and do that together. Alright, so in this example, we're finding the limit as x approaches negative 2 of x cubed minus x squared plus 6x minus 10. First of all, you have to ask yourself, is this a polynomial? And yes, it is. It's positive integer powers of x, or this last term is a constant term, and so this is definitely a polynomial. According to what we just set up here, any polynomial, the limit as x approaches a number of any polynomial can be determined by simply replacing all of the x's that we see in the polynomial with whatever number x is approaching. In this case, x is approaching the number -2, so we can find the limit very easily by replacing all the x's we see with a -2. And then we just compute that expression. -2 cubed is -8, minus -2 squared is 4. I'd get a -12 and a -10. And let's see, that would be -12, that's -24, that'd be -34. So the answer to this problem would be -34. Let's look at the next example together. We're doing the limit as x approaches 5 of x squared plus x plus 20 divided by 3x minus 5. Now we have to ask ourselves, is this a polynomial? Unfortunately, it is not. What kind of function is it? It's a rational function. It's one polynomial, namely x squared plus x plus 20, divided by another polynomial, 3x minus 5. And that means that it is a rational function. We can't use direct substitution, at least as far as we've gotten, and that's because it is not a polynomial, but we could go ahead and use the quotient law of limits. Remember, what the quotient law says is that the limit of a quotient is the same as the quotient of the individual limits, at least provided that the limit in the denominator does not turn out to be 0. So I'm going to go ahead and break this up into the limit as x approaches 5 of the top divided by the limit as x approaches 5 of the bottom. Now I want you to think about the top. The limit as x approaches 5 of x squared plus x plus 20. Well, if we just consider this function that's in the numerator, that function is a polynomial. And what does that mean? It means that to find the limit on the top, we get to use the direct substitution that we talked about here. So to find the limit of the top, all I have to do is replace all of the x's I see with the number that x is approaching, in other words, with 5. So in the top, the limit would be 5 squared plus 5 plus 20. Now let's consider the bottom. 3x plus 5 is also a polynomial. So I can also use direct substitution in the denominator. I simply replace the x I see with the number 5, and we would end up with, let's see, 25 plus 5 plus 20 would be 50 in the numerator, over 15 plus 5 would be, that should be a minus 5, excuse me. So this should have been a 3x minus 5, and this should have been a 3 times 5 minus 5. So in the denominator, I would end up with 3 times 5 is 15, minus 5 would give me 10. So I end up with 50 as the limit in the top, 10 is the limit in the bottom. Notice in particular that the bottom limit did not turn out to be 0, and that means that I was allowed to use this quotient law in order to determine the limit. So let's go ahead and compute this. 50 divided by 10 would be 5, and the answer to my problem then would be equal to 5. Now, just as we did in the case of polynomials, notice that when I was figuring out the limit of this rational function, that right at this stage in my series of steps, I have something that looks exactly like the original rational function, with x replaced with the number that x is approaching, with x replaced with 5. So just like with the polynomials, to find the limit of a rational function, we can simply use direct substitution and replace all of the x's with the number that x is approaching, as long as the number in the bottom, the limit in the bottom, does not turn out to be 0. So this question down here, what kind of function is this? We actually already answered that. This is a rational function. It's one polynomial divided by another. And in general, we could use the same argument for any rational function. If p of x and q of x are polynomials, p of x over q of x is going to be a rational function, and the limit as x approaches a of p of x over q of x would be the same as the limit of the top. It's a polynomial, so we use direct substitution. So we get p of a in the top over the limit as x approaches a of the bottom. The bottom is also a polynomial, so we use direct substitution and get q of a. That means that to find the limit of this rational function, one polynomial over another, all we have to do is replace all the x's we see with an a. Now there is a little proviso here when we're talking about a rational function. Remember that the limit that's in the bottom here has to be something that is not 0. So I'm going to put down here, provided that q of a, that's the limiting number in the bottom, is not equal to 0. So provided q of a is not equal to 0. Another way of saying the same thing is that we just plug in a in place of or for x. Again, we could call this the direct substitution rule. And let me just summarize what we've said on this page. If we are looking at the limit of a polynomial or the limit of a rational function, we get to use this idea of direct substitution and simply replace all the x's we see with the number that x is approaching, a in the general case. And the only provision is that if we're dealing with a rational function, we want to be sure that the denominator is not equal to 0. If it is equal to 0, it doesn't mean that it's impossible to find the limit or that the limit doesn't exist, but it just means that we cannot use direct substitution. Okay, let's go ahead and look at the next slide and see what that is about. Well, direct substitution is fantastic and fast when it works, but some limits cannot be done by direct substitution, and that's what I want us to look at next, is an example that cannot be done that way. So let's look at this one. The limit as x approaches 3 of x squared minus 2x minus 3 over x minus 3. And your initial reaction might be, hey, that's one polynomial divided by another polynomial. That's a rational function, so I should be able to use direct substitution. And it's perfectly fine to go ahead and try to do that. So we might start out by saying, oh, I'm going to use direct substitution, and I'm just going to replace all of the x's I see with the number that x is approaching, namely 3. So let me do that. I have 3 squared minus 2 times 3 minus 3 in the top. And in the bottom, I replace x with 3, and I get 3 minus 3. And you may already see that there's a problem. The top actually looks like it is 9 minus 6 minus 3 is 0. That's okay to have a 0 on the top, but notice that we also have a 0 on the bottom, and that is what is trouble for us. So here is trouble. And why is it trouble? Because we already said that the only way we can use direct substitution is if the denominator, our q of a, doesn't turn out to be 0, and in this case it does. This particular expression, 0 over 0, when we try to find the limit and we see that the top is going to 0 and the bottom is going to 0, is what is referred to as an indeterminate limit. That is the technical term for it. And what that means is not that we can't determine what the limit is, but we cannot determine the limit in the present form that we're given, that we have to do a little bit of work to figure out what the limit is. So this is referred to as an indeterminate limit. That is the technical term. I often tell students to think, that means that I can't tell yet what the limit is, that I have to rewrite. Maybe I'll put down here, must rewrite in order to determine the limit, or perhaps even to determine that the limit does not exist. Notice some people think, oh, 0 over 0, can't I just cancel the zeros and I would end up with 1 as the limit? And the unfortunate problem is that it depends on how fast the top is approaching 0 and how fast the bottom is approaching 0, what the overall limit will end up being. And the overall limit may not be 1, and in this case we'll see that it is definitely not equal to 1. Well, okay, we can't use the quotient rule because the limit of the bottom is going to 0. We have to try to rewrite, and the only way we really have to rewrite is to try and simplify the expression that we're asked to find the limit of. So I'm going to rewrite limit as x approaches 3, and notice that the top is a quadratic expression, and we may be able to factor it. I'm hoping that I can. So x squared minus 2x minus 3, well, that would factor into two binomials, each that starts with an x. Let's see, I'm going to need a negative and a positive for these numbers to multiply to a negative 3. And it looks like to come out with a negative 2x for the middle term, I would need an x minus 3 for one of my terms and an x plus 1 for the other term. The denominator of my expression is x minus 3. I can't factor that, so I'm just going to throw parentheses around it. Notice that this expression simplifies because I have a like factor in the top and in the bottom. So I have a factor of x minus 3 in the top that I can cancel with a factor of x minus 3 in the bottom. Now in algebra, we are a little bit sloppy and we just cancel those two things. Actually, we cannot cancel these factors unless they are both non-zero. If these factors are equal to 0, we are not allowed to cancel. What I want to remind you about is that when we are finding a limit as x approaches 3, we are never allowing x to quite equal 3. So x may be very close to 3, it might be 3.00001, but it is not equal to 3. And for any value of x that is not equal to 3, x minus 3 will be something that is not 0. If x equals 3.1, then 3.1 minus 3 would be 0.1. That is not equal to 0. So for the values through which x is running, through which we are limiting, for all those values where x is getting close to 3 but never quite equal to 3, the factor x minus 3 is non-zero, and so we are allowed to cancel these. I have some non-zero factor over an identical non-zero factor that's just equal to 1 in a different form, and I can cancel those two things. Let's go ahead and rewrite then and say that that means the limit of this more complicated expression is exactly the same as the limit as x approaches 3 of what's left, which is x plus 1. So now we're finding the limit of a much simpler expression. Not only is it a simpler expression, but what can you say about the type of function this is, x plus 1? It is a very simple polynomial. And if I know that I'm finding the limit of a polynomial, what do I get to do? Remember, then we can use direct substitution. So to find this limit is actually quite simple. All we do is replace the x we see with the number that x is getting closer to, namely 3. And so the limit as x approaches 3 of x plus 1 would be 3 plus 1 using our direct substitution, and that gives me 4 as a final answer. Notice, just as I mentioned before, when we had 0 over 0, this indeterminate form, it's tempting to want to cancel those zeros and say, oh, that's just equal to 1, but that would have been the wrong answer. The limit of our original expression, our rational function, turns out to be the number 4. Well, this is a nifty way to find the limit of something that could not have been done by direct substitution. You get an indeterminate form. You can't tell what the limit is if you simply substitute into the original expression. To understand this a little bit better, we might try to go ahead and graph it. And that's what I would like us to do next, is to graph this function y equal x squared minus 2x minus 3 over x minus 3. So let's try that. We're going to graph y equals x squared minus 2x minus 3 over x minus 3. Now, to graph a function, we need to know what the domain is. And if I look at this function, it's a rational function, and the domain would be all values of x except any values that make the denominator 0. So just notice that the domain of this function would be all real x except for the x that makes the bottom 0, except for x equal 3. So it would be all real x not equal to 3. If I want to graph this, of course I could do it by making a table of values, but it would be easier to simplify it in exactly the way that we did when we worked on the limit. If I were to go ahead and factor the numerator, I would end up with x minus 3 times x plus 1. For x's that are not equal to 3, I could cancel those two factors, and y could be rewritten then as x plus 1, but we have to artificially add the fact that these two expressions are equal as long as x is not equal to 3. That way our two expressions have exactly the same domain. So what we would be asked to graph is the function y equals x plus 1, where we allow x to equal any real number except for 3. If I didn't worry about this domain restriction, x not equal to 3, y equal x plus 1 would be pretty easy to graph. It's a linear function. It has a y-intercept of 1, and it has a slope of 1. So I would go up 1 and over 1 to get to another point on the graph. And I would end up with a straight line that looks something like this. However, this would be the graph of y equal x plus 1 with no restriction on the domain. We want to add this restriction that we don't want x to be equal to 3. Well, how do I show that on the graph? Well, we want to go ahead and show every point on the graph with x coordinates equaling any real number except for 3. So right at x equal 3, I want to indicate somehow that I want that point corresponding to an x coordinate of 3 to be missing on my graph. How do I do that? I just put a little open circle, and that shows that that particular point is missing. If I plug 3 into my function, I would get 3 plus 1 would be 4. So we're omitting the point x equal 3, y equal 4, 3 comma 4, that pair from our graph. So this is the graph of this function, x squared minus 2x minus 3 over x minus 3. If I were to try to find the limits from the graph, how would I do it? To find this limit from the graph, I would look at the limit from the right and from the left separately. So first I'd look at the limit as x approaches 3 from the right. I would plug values that are slightly larger than 3 into the function, go up to the graph and over to the y-axis. And my question is, as x gets closer to 3, do the outputs to the y values collect around some one number on the y-axis? And it looks as if the outputs are getting closer and closer to the number 4. If I were to look at the limit as x approaches 3 from the left side and choose something a little bit less than 3, I go up to the graph and over, I hit some y value, and I can see that as I choose things that are closer and closer to 3, but slightly smaller than 3, the y values are getting closer and closer to the number 4. So as I approach 3 from both the left and the right, the y values are collecting around one number on the y-axis, namely 4, and that shows again that the limit of this function is equal to the number that we found algebraically. It's equal to 4. Okay, I would like you to try the next problem. It's the limit as h goes to 0 of a rather complicated expression involving h. Usually we've used limits as x approaches some number exactly the same thing if we use a different letter. But go ahead and try to find the limit by direct substitution the way that we did before. And if it cannot be found by direct substitution, try to rewrite in a way that you can find what the limit is. Stop the video, give it a try, and then we'll go through it together. Okay, you've had a chance to think about this one. Let's go ahead and try it together. If I were to just let h go to 0 in the top. And notice that the top is a polynomial. If I were to multiply this out, I would end up with 25 plus 10h plus h squared minus 25. Those would all be terms in a polynomial. So if I were to find the limit of the top, I could do so by just plugging h equals 0 into this. Since it is a polynomial, I would end up with 5 plus 0 squared minus 25. That would end up giving me 25 minus 25, or 0 in the top. In the bottom, if I found the limit, this is also a very simple polynomial, so I can just use direct substitution and replace h with 0. So I also get 0 in the denominator. Again, that means that we have trouble. We have a 0 in the denominator, which means that I cannot use the quotient law of limits in order to find this limit. You can only use the quotient law if the denominator ends up being non-zero. Furthermore, I have this same form that we talked about in the previous example. I have a 0 over 0 form, and that is referred to as an indeterminate limit. So because this is 0 over 0, this limit is called indeterminate, which means that I cannot yet tell what the limit is. I can't determine what it is in this form, but I may be able to rewrite my expression in a way that I can tell what the limit is. So we must try to rewrite in order to determine what the limit is or whether that limit exists. So let's go ahead and see if we can rewrite this. There are different ways to go about simplifying this rational expression that we have right here. And one way would be to use the fact that the numerator is really the difference of two squares. I have the quantity 5 plus h squared minus 25, which is 5 squared. So you may have done it that way. That would probably be the most efficient way. But most people would probably just think about foiling this out, 5 plus h times 5 plus h. Let's do it that way. And it may take a little bit longer, but it is probably what most people thought of. And if I FOIL that out, let's see, I'll get 25 plus 5h and 5h, 10h, plus h times h is h squared. It looks to me as if the 25s drop out in the top. Those add up to 0. So I am left with limit as h goes to 0 of 10h plus h squared in the top and h in the bottom. Now notice that there's a common factor of h in the top. I'm going to go ahead and pull that common factor out. What would I be left with in the parentheses? I would have a 10 plus an h, and I still have an h in the denominator. Well, if you just plug h equal to 0 into the top and into the bottom, you're still going to get 0 over 0. You still get this indeterminate form. But how else could I simplify this? Well, I could cancel the factor of h that's in the top and the bottom. Again, remember in algebra we're maybe a little bit sloppier and we just say, oh, we have an h in the top, we have an h in the bottom, those cancel. Remember that we're really only allowed to cancel these as long as they are non-zero, as long as h is not equal to 0. But luckily, when we are doing a limit, h is getting closer and closer to 0, but remember that it is never quite equal to 0. So it may be something very small, but it will be something that's non-zero, and so if h equals, say, 0.01, you have 0.01 over 0.01, that's equal to 1 in a special form. So we are allowed to cancel those, and the limit of this expression with the h's will be the same as the limit once we have canceled the h's. So it will be the same as the limit as h goes to 0 of 10 plus h. Now let's look at the expression that we have left. What we have left here is a polynomial, And since it's a polynomial, we can find that limit by direct substitution. So I can go ahead and just replace the h I see with what h is approaching, namely 0. So I get 10 plus 0, and that gives me a final answer of 10. Okay, let's go ahead and look at a couple more examples that involve limits that maybe give us some sort of trouble that we can't just automatically do by direct substitution. So on the next page, I'd like us to look at this limit, and let's do it together because it's kind of a tricky one. Limit as h goes to 0 of u divided by square root of u plus 49 minus 7. So let's go ahead and see if we can see what's happening in the top and what's happening in the bottom as u gets closer and closer to 0. Technically the top is a polynomial, so we can go ahead and just replace the u in the top with what u is approaching, namely 0. In the bottom, it is not a polynomial because we have this square root. It's really a root expression. You can use the difference law of limits and the root law of limits. I'll let you go ahead and fill in the details of that. Ultimately, we will end up just allowing u to go to 0. So I'll let you fill in the steps that would go in between here, but the bottom is going to be getting closer and closer to 0 plus 49 minus 7. And if we compute that, I would get square root of 49 is 7 minus 7 gives me 0. So notice that once again, I have an indeterminate form of 0 over 0, meaning indeterminate, meaning that I cannot yet tell what this limit is going to be. And the reason that we can't tell again is that the top of this expression is approaching 0, the bottom is approaching 0, but they may be approaching at different speeds. They sort of battle each other out. And so until we rewrite, we cannot yet tell what that limit is going to be, and we must try to rewrite by somehow simplifying the expression. Well, this particular example is a little tricky because there's no way to really factor, say, the denominator the way that we factored the numerators in our last two examples. So we have to find some way of rewriting this. And you might remember from algebra that when you had a radical expression, a square root expression like this, and two terms in the denominator, you could do something called rationalizing the denominator. It's a way of getting rid of the square root in the denominator. And so let's go ahead and write down that this is equal to the limit as u approaches 0. I'm going to leave the top alone since that already looks as simple as I can get it. And in the bottom, I'm going to write square root of u plus 49 minus 7. That's the expression that I have in the bottom. And I want you to think back to algebra or your pre-calculus class. What was the trick we used to get this u plus 49 out from underneath the square root symbol? You may remember that it had to do with what were called conjugates. We take this expression and we multiply by exactly the same thing, except that instead of a minus sign between our two terms, we put a plus sign. And this was what was referred to as the conjugate of the expression square root of u plus 49 minus 7. Same exact expression, but we flip the sign that's between the two terms. Well, am I allowed to do that? Can I just multiply the denominator of my expression by something and expect it to be the same expression? No, I can't. If I multiply the bottom by this expression, I have to also multiply the top by that expression. And you might think, oh, well, now I have a square root in the top, and that's true, but at least this will end up getting rid of the square root expression that is in the bottom. So let's see how this works then. I'm going to go ahead and leave the top as this sort of long mess, u times square root of u plus 49 plus 7. And in the bottom, I'm going to FOIL out. When I multiply square root of u plus 49 times another square root of u plus 49, square root of something times square root of that same thing is just that thing. So when I multiply these two terms together, I'm going to get u plus 49, and the square root will disappear. When I do the outer two terms, I get a plus 7 times square root of u plus 49, and when I multiply the inner terms together, I get a minus 7 times square root of u plus 49. And then when I multiply the last together, I get negative 7 times 7, negative 49. And you notice that this does indeed get rid of that square root expression because it appears in a 7 root u plus 49 and a minus 7 root u plus 49. So those two things add up to 0 and drop out. What else drops out in the denominator? I have a positive 49 and a negative 49, so those also add up to 0. And you notice that I'm left with just a u in the denominator. I have a u that's in the numerator as well. Those factors will cancel out. So this u and this u will really give me just a factor of 1. And remember again, u is approaching but never quite equal to 0, and that's what's going to allow me then to cancel these u's that are in the top and the bottom of my expression. So what will I ultimately be left with? I'll be left with limit as u goes to 0. I'm going to write that step before I cancel these u's of u times square root of u plus 49 plus 7 over the u that's left in the denominator. Now we're allowed to cancel those u's. I sort of did that ahead of time, but now we can cancel those u's, and I am left with just the limit as u approaches 0 of square root of u plus 49 plus 7. I'm finally left with something that I believe will not give me an indeterminate form. It was this u that was in the numerator and the denominator, that factor of u was what was going to 0 in the top and the bottom and giving me this 0 over 0. Technically, again, because this is not a polynomial, I shouldn't just automatically jump to the conclusion that I can use direct substitution. I should go ahead and use my limit laws. And what would the limit laws say? Well, I have a sum, so I can say the limit of the sum is the same as the sum of the individual limits. So limit as u goes to 0 of square root of u plus 49 plus limit as u goes to 0 of 7. This is a square root, so I can use my root law to pull this limit sign underneath the square root. We said that the limit of the root is the same as the root of the limit. And this limit is the limit of a constant. Remember, that was one of our building block limits, and the limit of a constant is just that constant. So the limit as u goes to 0 of 7 is just 7. And now if I look at what's underneath the square root, this last limit that I have to do, this u plus 49 is a polynomial, since it doesn't have a root in it. And so now I'm really allowed to go ahead and use direct substitution. The limit as u goes to 0 of u plus 49 would be square root of 0 plus 49 plus 7. And square root of 49 would be 7. And so I get 7 plus 7, and that would end up giving me 14 as a final answer. In particular, notice that we didn't end up getting 1 as an answer, even though numerator of our expression was going to 0 and the denominator was going to 0. They approach 0 at different rates, sort of battle each other, and we end up with a final answer of 14. Okay, let's go ahead and think about the next example. It's really rather different, and it will give us another indeterminate form, but of a different type than the 0 over 0. Before we do that, however, I want to go ahead and talk a little bit about fractions. Because of calculators, people don't really think in terms of fractions very much these days. So I want to remind you about fractions. So I'm going to go off our book here and just remind you of what happens to fractions as their denominators get smaller. So remember, if I have a fraction maybe of the form 1 over x, something like that, as this x value gets smaller, I want us to think about what happens to the size of the fraction. And for the time being, I'm going to insist that x be something that is positive, and I'm going to allow it to get smaller. I'll say positive, but getting smaller. Let's see what happens as I do that. If you want to, you can make a little table of values where here's our x value and here's 1 over x. If you put something like 1 in place of x, you'd get 1 over 1, which would be equal to 1. Now I want to let x get smaller. Suppose I put in something like 0.1. Well, if I do 1 over 0.1, remember 0.1 is the same as the fraction 1/10. And if I invert and multiply, I end up getting 1 times 10 over 1 would be equal to 10. So that's a fairly large number. So as this denominator got smaller, notice that the output of 1 over x gets larger. I go from an output of 1 to an output of 10. If I put in something like 0.01, I would have 1 over 0.01. That's 1 over 1/100th. And when I invert and multiply, that would give me an output of 100. If I continue to let my x be positive but getting tinier, I would end up then with values that continue to get larger. 1 over 0.001 would be 1 over 1,000, and that would end up giving me 1,000 when I invert and multiply. So as this gets closer and closer to 0 through positive values, through values that are a little bit larger than 0, notice that the outputs are getting larger and larger. The outputs are actually going towards positive infinity. So as the denominator gets smaller up here, I'm going to put limit as x approaches 0 from the right of this expression. The top stays fixed at 1. The bottom gets smaller and smaller. Say smaller and smaller. And what does that mean about the overall fraction? The overall fraction is actually approaching positive infinity. If we allowed x to approach 0 from the left, it would be a similar kind of situation, except that these inputs here would all be negative, and that means that the outputs would all be negative. So you might check yourself that if we were doing the limit as x approaches 0 from the left of 1 over x, well, the top would stay fixed at 1. The bottom is getting smaller and smaller in size, in absolute value. The values are actually increasing, but in terms of the absolute value, we could say the bottom is getting smaller and smaller. I'm going to say, but negative. Actually, when we say smaller and smaller, we mean that the absolute value is getting smaller and smaller, but the expression would be something that's negative. And since we have a positive in the top and a negative value in the bottom, the overall sign of our expression would be something that is negative. positive divided by negative is negative, and yet getting larger and larger in size, because this same idea happens. This would actually be approaching a negative infinity. If you're not sure about that, you can fill out a little table just as we did before, and instead of putting in 1, try -1. You'll get -1 as an output. If you put in negative 0.1, you'll get -10 as an output. Negative 0.01, you'll get -100 as an output, and so on. So these are approaching 0 from the left, and the output values are now approaching negative infinity. Well, that will be some good background for the example that we are going to do next. So let's go ahead and look at that second example on our page. This example. And here we're looking at the limit as x approaches 0 of 1 over x squared minus 1 over x to the 4th. So let's go ahead and see if we can decide what's happening to each of these fractions as x gets closer and closer to 0. Notice that this first fraction is 1 over x squared. As x gets smaller, approaches 0, either from the right or the left, the top of this fraction is staying fixed at 1. Now what's happening in the bottom of this fraction, as x approaches 0, you could think of x approaching 0, say, from the right. So x might be 1, and then 0.1, and then 0.01, and so on. It's a smaller and smaller number, so this x squared is getting smaller and smaller. If x gets smaller, x squared is getting smaller even faster. So the bottom is getting smaller and smaller. And whether I approach 0 from the right through positive values or from the left through negative values, remember that we are squaring our x value. So whether x is positive or negative, when we square it, what will its sign be? Its sign will be something that is positive. So the top is staying fixed at 1, the bottom is getting smaller and smaller, but a positive value. When we invert and multiply those small fractions that we have in the bottom, we are going to end up with an overall fraction that is getting larger and larger, just as we talked about on the previous discussion. So this fraction is actually approaching positive infinity. Well, let's think about the other fraction that's in here. We're going to be subtracting a fraction that is, again, fixed at 1 in the top. The bottom is going to be a small number, either positive or negative. When I raise it to the 4th power, it's an even power, so I'll get something that is definitely positive in the bottom. And when you take a small number and raise it to the 4th power, you get an even smaller number. For example, if I have 0.1 and I raise it to the 4th power, I'm going to have 0.1 times 0.1 times 0.1 times 0.1. That will be something that is a very small decimal. So the bottom is getting smaller very quickly and is positive. That means the overall fraction, positive divided by positive, is going to have a positive value. And if I have a fixed numerator and a smaller and smaller denominator, the size of the fraction gets larger and larger. So when I think about this limit, I'm in sort of a little bit of a quandary, because this first fraction is approaching positive infinity. It's getting to be a larger and larger number. This second fraction is also approaching positive infinity. It's getting to be a larger and larger number. But remember, infinity is not a specific number like 10,000. So we can't simply subtract these and say, well, then the limit must be equal to 0, because infinity is really just a concept for something that is getting larger and larger, and these fractions may be going to infinity at different rates. It's a little bit like the indeterminate form that we talked about here, where the top was going to 0, the bottom was going to 0, but possibly at different rates. The same thing is true here. I have infinity minus infinity, but if this expression, I should say, is going to infinity faster than this one, or vice versa, then perhaps this one will sort of win the battle and get large faster, or maybe this one will win the battle and get larger and larger faster. In other words, this is another type of indeterminate limit. So I'm going to say this limit is also indeterminate, meaning that we cannot determine what the limit is when it is in this form. This is true really for any kind of limit that has two infinities of the same sign that are subtracted. So if I had something like negative infinity minus negative infinity, that would also be an indeterminate limit. Well, let's go ahead and see if we can rewrite our expression in a form that allows me to find what this limit is equal to. So I'm going to go back to my original limit, and I'm going to put, I want the limit as x approaches 0 of 1 over x squared minus 1 over x to the 4th. And part of the problem with figuring out what this limit is was that we got an infinity minus an infinity. Let's see if we could try to get out of that situation by combining these into a single fraction so that I don't have one term minus another term, but I just have a single fraction. So the first thing I'm going to do is try to combine these. That means that I need a common denominator. Well, what's the least common denominator for x squared and x to the 4th? We have to take the denominator of the highest power that we see, and so that would be x to the 4th. So I'm going to try to get both of these over x to the 4th. This is already over x to the 4th, so I'll just multiply this one by x squared to build that up to x to the 4th. But don't forget that I have to multiply the top by the same amount. And so this would be the same as the limit as x approaches 0 of x squared over x to the 4th minus 1 over x to the 4th. Now I can combine them into a single fraction. This would be the limit as x approaches 0 of x squared minus 1 all divided by x to the 4th. Well, now we can go ahead and try to figure out what this limit is. The top is the polynomial, so to compute that, I get to use direct substitution. So the top is getting closer and closer to -1. What about the bottom? The bottom is approaching 0. Well, okay, so the bottom is going to be getting smaller and smaller in size. It'll be a small number in place of x. I'm going to raise that to the 4th power. So whether x is approaching 0 from the right and is positive, or x is approaching 0 from the left and is negative, when I raise this to the 4th power, I will end up with something that is positive in sign. So the bottom is going to be getting smaller and smaller, and it's going to be positive in sign. And here perhaps I should use not an equal sign, but maybe an arrow. The top is approaching -1, the bottom is getting smaller and smaller but positive. And what would that mean about the overall fraction? What's happening to that? Well, what about the sign? The top is negative, the bottom is positive. A negative divided by a positive will end up giving me a negative for the overall sign. And what about the size of this fraction, the absolute value of this fraction? Well, if the top is fixed, but the bottom is getting smaller and smaller, according to the discussion we had earlier, the overall fraction in size, in absolute value, will be blowing up, will be getting larger and larger. So a fixed top over a tinier and tinier bottom means the overall fraction is getting infinitely large in absolute value. But the overall sign is negative, and so my answer would actually be a negative infinity. Why is it a negative infinity? We could actually go back to our discussion that we had up here and see why that's true. This fraction had x raised to the second power, whereas this fraction had a denominator of x raised to the fourth power. When x is approaching 0, getting smaller and smaller, this one is actually getting smaller faster than this one. And that's because you're taking that tiny number and you're raising it to a larger power, to the fourth power. So in this battle that we talked about, yeah, the first fraction is going towards positive infinity, but the second fraction is growing towards positive infinity much faster. It wins the battle. So although this one was getting infinitely large, this one was getting infinitely large even faster. And that meant that overall, this is a large number minus an even larger number. Overall, this one wins the battle, and we end up with minus infinity as a final answer. You could try yourself switching the orders of these two fractions to find the limit as x goes to 0 of 1 over x to the fourth minus 1 over x squared, and check for yourself that you'll end up with the first fraction going to infinity faster, and so you'll end up with an answer of positive infinity instead of negative infinity. Okay, let's go ahead and look at